Что, так уже все готово?
Не-не-не, в смысле, я говорю, я не хочу использовать, мне просто было интересно. Тут есть
Вроде да.
Потому я так и не нашел.
А нет, зато можно включать, значит. А тут нет.
Okay, let's start. So we'll have the last lecture by Dmitry Melnikov about knots and quantum mechanics. This is the same as with Professor Barata. I mean, so this is the last lecture, and Dima will leave actually today. So advice, if you have some questions or something to discuss, better to do it or during the lecture or after the lecture.
During the coffee break, right?
Yeah, during the coffee break, yes. I mean, so. Okay, so please.
Okay, so far I think, I'm not sure about my lectures, but it seems like a very nice school and very, very nice set of lectures. And I enjoyed it pretty much, and so unfortunately I have to go and I will miss some of the courses. Okay, so let me just remind you where we finished last time. So there was a lot of different words about different subjects, but what I wanted to do at the end was to give you some kind of model based on a set of axioms, which, more workable than, let's say, Chern-Simons theory. The Chern-Simons theory, even though it's sort of trivial, it's also a complicated theory if you want to do calculations. And just reminding you that in Chern-Simons theory, we can construct states as path integrals. So you just take a path integral over gauge configurations, and then you can limit this gauge configuration to satisfy certain boundary conditions at a chosen boundary, which you can call a Cauchy slice if you wish. So your state will be a function of the chosen boundary, and of course it will also depend on the manifold. So this is a 3-manifold where you compute this path integral. So this would be a state, a calculation you need to do in Chern-Simons theory if you want to construct your state. And in particular, the most simple example, you just take a 3-ball, so a 3-dimensional space bounded by a 2-sphere, and you compute this integral for gauge configurations inside the sphere. So this is, this particular case is trivial, but in general, I will want to put some charges on the surface of the sphere, and these charges will be connected by some Wilson lines in the interior of the sphere. So this is an example of a state. And what I proposed on the last lecture was a simpler model, which I called like 1D topological quantum field theory or topological quantum mechanics, where I basically have an equivalent theory, but which works in a more direct way. You do not need to compute any path integrals, but all amplitudes that you compute in this theory are just the same amplitudes. And for example, a state like this, the way I was representing it was just a collection of points. Well, I was drawing some line just to tell you that they actually belong to the same boundary. So they kind of join together, and they all, this collection is a certain Hilbert space, and then vectors in this Hilbert spaces, they are lines that connect these points, and these lines can actually, it's a bit more complicated. So the lines can interact with each other. And the way to think of this is probably in terms of some integrable model, a spin chain. You have spins here, and they have some time evolution, so they can interact. And this crosses here, the crossings, they are some certain interactions of these particles. But actually, the particles can also annihilate at certain moments of time and so on. So that's kind of a map from one theory to another, and I gave a set of simple rules how to calculate the states. So you just introduce That's an example with 4 points. You can put any even number of points together to construct a state. And then the rules to compute a state, you choose a basis. In this case, I said I'll choose a basis of diagrams, which I call a temporally basis, which has lines without intersections. And I use this to define orthonormal basis. And then if I want for any state, this is just an example for 4 points, which corresponds to dimension, Hilbert space of dimension 2. I can do the same for high dimension. This is something that will appear in my talk today. So basically, if you want, given a state like this, you just glue one of the basis vectors on the other side. This produces some knot or a link, and then you use the rules of Jones polynomials to compute the corresponding amplitude, right? So just to give you like very brief example, I'll just compute the overlap of this state, which I'll call psi, right? So what is an overlap of psi and the state 0? So I just need to glue the state 0 from the other side, and there will be a normalization factor 1 over d. Well, so in this case, actually what it is a trivial knot, so it will be just proportional to factor of d, so factor of d will cancel. But in fact, since there are 2 twists here, in my formula, this produces just a phase. So that will be, this phase will be something like this. Maybe the sign is incorrect, I'm not sure, but that will be squared, okay? Because there are two loops like this that you have here. Then you can also glue the state 1 here and compute it in a similar way. And the easiest way to calculate is to remember the skein relation. You just, any intersection you replace by this linear combination. And this simplifies the diagram. Okay, and then at the end of the lecture, we started to consider some examples. And I will be interested in discussing entanglement. And so the states will be bipartite or tripartite. And the very basic example of a bipartite state was this. So I have 2 boundaries, which each of them represent a 4-dimensional Hilbert space. So here I have a 2-dimensional Hilbert space. I have a 2-dimensional Hilbert space here. So this is a state in the tensor product of these 2 Hilbert spaces. And as we discussed last time, this state, what you see here is basically an identity operator. So this state here is nothing but 0, 0 plus 1, 1. So you can compute this explicitly, and this was a homework exercise. I'm not sure you had time to do this exercise, but if you have time in the future, I think it's fun. Okay, and then you can do the same for more complicated states, and then you can start try to ask this question. So what does it really mean? But how topology, right? How these diagrams represent different types of entanglement? Well, okay. Let me start with we'll continue with the plan of my lecture today. So I will introduce this. I will discuss the possible entanglement classification using this approach. And I will also discuss some other things you can do with this kind of approach. I will discuss entropy inequalities and an example of a basic quantum protocol like quantum teleportation. So how things look in this language. So that's the plan. All right, so this is where we ended yesterday, right? So here you see some examples of bipartite states. This is just first preliminary, very basic classification. Obviously, if you have a situation like this where you have left and right are not connected, so the lines do not go from one boundary to the other. I do not draw these vertical lines here just to save time. This is a heuristic picture of, if you think of Chern-Simons kind of theory, so you have 2 spheres with 4 punctures, but Wilson lines do not go from one sphere to another. So you can compute explicitly the coefficients by the procedure which I just outlined here and see that this is just a 0, 0 state. And another basic example is the one on the board. You just get the identity operator or an example of a Bell state, of a maximally entangled state. And I also made a comment, well, you can just take this state and apply a braiding operation. It can be applied on the left or it can be applied on the right. How do I do this? So this is my state, and then I can act by a local operator on the left or on the right. What is an operator? So operator basically is another diagram. In this diagram I can, for example, apply something like this. It can be product of two braid generators. Right, so when I glue these two diagrams together, I get the diagram on the left, right, this one. Okay. But it turns out that braiding in this construction is just, this local braiding is a unitary operation. So why is it unitary? I showed it last time, but let me just show it again. So this is the operator. I think this is the operator. Then I want to compute Hermitian conjugate of that. Well, Hermitian conjugate of that was basically defined in such a way that it represents the inverse evolution to the evolution we see here, so it should go like this. More precisely, if you have Jones polynomials, then complex conjugation acts as by inversion of parameter A, because remember A was just a pure phase, so it is just complex conjugation inverts that. And in terms of the scaling relation, it means that it actually flips, right? It flips first diagram with the second diagram. So when you apply complex conjugation, I think I was trying to draw the. Thank you. So it's the other way around here. So then I have to change also here. Right, so when I apply complex conjugation, so this A becomes A minus 1, right? So I get A minus 1 identity plus A temporally lib. But just reminding you, I can just rotate all diagrams here 90 degrees. So what I will get is this diagram, which is the inverse of this operation, right? So complex conjugation also inverts the overcrossings and undercrossings, and also it has to change the order of products of the generators. So this is what happened here, right? So this is the operator, and this is the Hermitian conjugate of that. Well, if I glue this together, obviously I have topologically trivial configuration here. So that's an identity matrix as we just discussed, right? I hope you can see that. Okay, so local braiding operations, they are unitary here, and unitary operations, local unitaries, do not change the amount of entanglement, which means that this first this diagram here is also represents a maximally entangled state. Well, also notice that in this formalism, there is this, you can easily see the duality between operators and states. So this object here, you can think of it as a state. It's a bipartite state in the tensor product of two Hilbert spaces, or I can, well, actually, here it looks more like operator, because I said this is an operator, I applied it here, so it seems like also an operator, but I can draw this state in a different way. I can bend it, so I can draw it like this instead. Then it looks more like a state rather than an operator, right? But in terms of diagrams, I can do it without any problem and without really being concerned of applying complex conjugation and everything. So at the moment of computing all the amplitudes, things will work out automatically. So view this as a state, as an operator or as a state, and these are kind of two equivalent pictures. By the way, so relating to the lectures of João at this school, right, you can think of this identity state as the cyclic separating state in a von Neumann algebra. And then you have this, so this is the cyclic separated state. And you can think of some operators that act on this state, right? In my picture, this can be Braiding operators or whatever. So if I just apply an operator on the left or on the right, what I will get as a result is a new state, but the diagram for this state will be like this. So this means that I just start with a unique state and I generate the whole Hilbert space. Okay, or maybe I just generate a dense set in the Hilbert space by applying all operators on this particular state. And this particular state is very special because it is a separator state, a separating vector, because whatever I apply here, because it's identity operator, it will never be zero unless what I apply here is zero. Okay, that's kind of simple illustration of what was discussed today. But of course, here you think more in terms of more simple matrix algebras of type 1. Although I think there is, it is also connected to type 2 because Jones polynomials were actually derived from type 2 algebra. Okay, so we're still on the first slide. There's this last example. So you want to construct an intermediate example. So I don't want neither separable nor a maximally entangled state. So I want a state within some intermediate entanglement. So what do? I cannot apply unitary, so I cannot apply local braiding, but I can apply non-local unitary to do that. And non-local unitary in this case you can understand as exchanging the lines between or points between left and right, and which in particular can create this kind of tangling. So it is no longer braiding in terms of acting of local operations on left and right, but it is you can check explicitly. I haven't written the expression here, so I suggest to do this as an exercise just to convince yourself. So this is not just a diagram, it is certain expression. You will find actually that it also has only two components in the expansion and the basis, but the coefficients here will be different in such a way that it represents a matrix which is diagonal but not unitary. So all states which with intermediate amount of entanglement, they can be mapped to some non-unitary but invertible matrices. So all non-invertible matrices like this, they're projectors. They have some they have 1, 0 eigenvalue. So these are separable. This one have both eigenvalues non-vanishing and non-equal, and they will be you can make them. Okay, so there will be some complex numbers, phases. Okay, so now this was kind of preliminary analysis, and let's now try to do something more serious. And so first of all, you can say, okay, actually, you can draw as many diagrams as you want, and each of these diagrams will sort of give you some different different pattern, at least, of entanglement. So this is already a classification. But here is some conceptual problems from the point of view of people who do information theory. So they don't like infinite classification. So they want finite classification. So they want to say, okay, there's a finite number of entanglement classes. Why is that? Because, okay, you need to really solve certain problems, quantum tasks, and then you need to know, okay, I need to solve this problem, which kind of state do I use for that? And if like there's an infinite choice, it becomes unsolvable problem. So you want a finite classification. Of course, you want to have some complete classification. I will comment on that, whether the classification is complete or not. And well, there will be some technical problems, so this is related to the fact that we are working in something related to quantum groups. So there is this parameter k, and in fact the dimension of the Hilbert space has this, well, doesn't make very close friendship with this parameter k. So when k is sufficiently large and the number of punctures, number of lines is small, we may think of this as just regular spin 1/2 particles. But when k is small, then we may have some certain degeneracies in our Hilbert space. So then the problem becomes a bit more complicated. But this part I will skip. I will not be worried about this. I'll just always assume that k is either very large or maybe not even integer. Okay, so now I want to just starting from this initial idea, I'll just draw diagrams and try to explain kind of different entanglement classes, types with this. Yes.
So when k is large, you still get the difference very small compared to k, or is guaranteed that you don't have it?
So to have this problem of degeneracy, because in Wess-Sumino-Witten model, basically you have all this the primary operators, the number of primary operators in SU2 level k will be k plus 1. So you do not want to, with this kind of, so these lines here, they are spin 1/2 primaries. So if I draw many spin 1/2s, they can fuse to produce something with spin which is larger than k. So I do not want to have this amount of lines which is, can produce such particles. If the amount of lines is smaller, I will never have this problem. So I can just work in this subspace of larger Wess-Sumino-Witten. All right, so the idea is, the first idea that comes to mind is if I want to coarse grain my classification, how about I just look at, what is connected to what? So I have left and right, and I will not worry about, these details, how lines go from left to the right. What is important is that one line either goes from left to right, or it never connects left and right. And remember that any permutation, any local permutation is a Brayton operator, which is unitary, so that doesn't change the amount of entanglement. I will not worry about this, so I'll choose the most simplest configurations like planar graphs that connect different, well, this is for bipartite entanglement. For bipartite and tripartite entanglement, you can just work with planar graphs. And in certain sense, I can try to classify different types of entanglement with planar graphs or adjacency matrices of planar graphs. And here is the example of what you can do, let's say for 6 points, right? So these are all possibilities of connections between left and right, modular local Brayton. Okay, this is all you can have. So the question is, okay, does it make sense, this kind of classification? And the classification I want to compare with is this of stochastic local operation and classical communication, right? This one. So this one tell me that if I have two Hilbert spaces, well, maybe it's on the next slide. I think I discussed this yesterday. So just to remind you, so if the classification of the bipartite entanglement with this lock is very simple. It actually tells you if you have a pair of Hilbert spaces, well, let's take them both of dimension m, then there should be m classes of inequivalent classes of topological, of quantum entanglement. Right, and this classification is modular local invertible operation. So not only unitary, but also any invertible operation that you can apply on the left or you can apply on the right. So if we try to do this for 4-point Hilbert spaces, which should represent qubits, I can draw 3 diagrams, but we expect 2 classes. Well, here, what happens here is actually this model, which inherits it from Chern-Simons theory, has certain non-linearity in the sense that the dimension of the Hilbert space does not depend linearly on the number of points. And I told you before that kind of naive calculation which does not take into account possible degeneracies due to k is, for two endpoints, is the nth Catalan number. So this is how we compute, which gives you 1 for 0 points, 1 for 2 points, and 2 for 4 points, and 5 for 6 points. And the consequence of that is that actually the first and the second state here are actually the same states. And how can we see that? Well, if there are only two lines that connect the two spheres, it means that well, let me just use some space here. So in this situation, I can think of, cutting this diagram in the middle and doing something like insertion of a completeness relation. Right, so I have to cut this diagram into two and insert complete basis in the middle. But the basis in the middle will actually be corresponding to a sphere with only two punctures. And this is dimension 1. So it means that there's only one basis state, which automatically implies that this state is separable. I can just cut it in the middle. So the second diagram here is actually equivalent to the first diagram. And I will generalize this for more generic situation in the next slides. So there are only two inequivalent classes of diagrams, which you can again relate with either Bell's type of entanglement or the separable states. So now we want, of course, this is a trivial result. We want to generalize it to any dimension of the Hilbert space, like M. So you can first try to go to 6 punctures. In this case, unfortunately, as I said, the dimension of the Hilbert space is a nonlinear function, so it grows exponentially with the number of points. In this case, the dimension, you go from 2 to 5 immediately. But if you try to draw the diagrams, I already showed this in one of the slides, you have only 4 diagrams in inequivalent. Actually, there are only 3 inequivalent diagrams in this case, rather than 5 classes. So apparently it doesn't work. But the first problem which I mentioned here is also that you cannot really have a classification for any given dimension of the Hilbert space. So there's another way to do this, and for that I will do the following. So I'll explain you how to, so far the lines in my diagrams, they were representing particles of spin 1/2, and you can ask, okay, why should I really limit myself to particles of spin 1/2? Can I have like particles of other spins? So how I can do this in my model? So for that I can use the so-called, well, in some literature this is called Jones-Wenzel projectors or symmetrizers, and what they basically do, they tell you how to, well, let's say, if you have a product of, tensor product of two-dimensional spaces, how you can project that onto subspace of a given spin. For example, take 2, right? You have a doublet and a doublet, so it's dimension 4. But dimension 4 is a triplet plus a singlet. So how do you, for example, can extract a singlet? Well, actually, or triplet. Singlet is easy. So singlet means that it's well, 2 anti-parallel spins. Total spin is 0, and the original temporally projected dice is exactly that. So you can think of 2 particles annihilated, and then which means that they fused to produce a spin 0 state. So that's a projection on a singlet. Well, if you want to project on a triplet, just take the full thing and subtract the project on a singlet in such a way that you make a projector which is orthogonal to this projector. So this projector will exactly do the job. You can check that. First, this is a projector, and it is orthogonal to the projector P1, which is a singlet. Right, so P1 times P3 is 0. And there's a formula, there's a recursive formula how you construct such a projectors. So I'll just flash it here. And for if you want to produce, any representation, any spin, if you want to, you have n lines and you want to produce spin n minus n and n divided by 2. So you just take this procedure recursively using this formula. You can find this in the notes and later if you want to play with this. But it's also kind of a simple exercise to learn a little bit about representation theory if you're not very much familiar with it. Okay, so now I'll just remember that, well, if I have two, so triplet state is kind of interesting because if I start fusing, remember that the way to determine, another way to calculate the dimension of the Hilbert space is take the charges with certain, well, each one with its spin, and try to find how many singlets you can form with these charges, with this spin. So if I do this with 4 triplets, there will be 3 ways to form a singlet. And so instead of making my diagram out of spin 1/2, I can just try to make it out of spin 1. So this is the idea. I just take lines and then I project these lines. Every pair of lines I project onto a triplet representation, spin 1, and then you can check that there will be only, well, there will be a number of diagrams, but as far as non-equivalent ones, you'll have only 3. So this is what we want. You can ask why there are no lines, why there are no diagrams with more lines broken here between left and right. This is the same effect that as we had for the states for spin 1/2. In that case, if you break more lines with spin 1, you'll get a separable state. So there are only 3 independent. And then you just generalize this for, you go then to spin 3/2, which will have dimension 4, spin 2 will have dimension 5, and so on. So kind of summarizing, this is the classification, right, of different types of entanglement. It's a bit, this space lacks between the lines of this rows of this rows of this table, but what I do here, I only draw half of the diagram because I said this lower half of the diagram is not important because it is there, but it is the same for all diagrams, so, which means that for spin 2 I draw just this, but you should duplicate the diagram and mentally and then the additional pair of lines here, the same for the other classes. So the classification will be exactly this log one, and if you really look at these pictures, you actually understand why this is the same as slog classification. Yes, please. This is just a bipartite case. Exactly. So that's my comment. Exactly. So that's you can see how Schmidt decomposition is. How you find Schmidt decomposition in this presentation? So this is what? No. So this guy is maximally entangled, and in terms of Schmidt decomposition. So what is, again, so what is Schmidt decomposition, right? You will have a state, if you write a bipartite state, then you just write it as some sum with some square root of lambda, which are positive or non-negative. And here the base is I first qubit, the second qubit, sum over I, right? And so the entanglement class in the slog classification will be the number of non-zero lambdas. So when all lambdas are non-zero, you have matrix of the maximal rank, and this corresponds to the maximal rank matrix. You just have complete connection between left and right. Here you have one eigenvalue less. I mean, there's one zero eigenvalue. Here are the 2 zero eigenvalues, 3 zero eigenvalues. I think the diagram is kind of pretty self-explanatory in this sense. So each additional eigenvalue is, well, in this particular diagram, this is an additional pair of lines that connect the two. Well, now there is a problem that Frank mentioned, that there is the bipartite entanglement is kind of trivial, so it's very easy to classify it in normally, and also in this case, it was even a bit harder than just in ordinary quantum mechanics. And the statement that is usually made that you cannot, now I'll just comment about multipartite entanglement, you cannot explain multipartite entanglement in terms of the bipartite, just the bipartite ones. And unfortunately, I will not be able to solve this problem. I will just mention that somehow it is indeed difficult. So let's look at the tripartite situation. So that will be, if you try to play the same game and just look this basic way of classifying, now ignoring any intrinsic topologies that different lines can form, you'll have only 7 diagrams. But again, you'll have this well, sort of degeneracies. Like here, for example, you have only 2 lines connecting 2 subsystems, which means you can cut it. So this second state is equivalent to this one. This is also the same state. This is the same state. So there are 4 completely separable classes. Well, this is obviously, you should call it some kind of generalization of the Bell class. There's 2 qubits are in the maximally entangled state, and there's a third one which is not entangled. And this is the same as the 5th one. So the only non-trivial, like real, genuine tripartite entanglement is this one. So you can ask which kind of entanglement is this represents, and that's a state from a GHZ class. You can play the same game and compute explicitly the coefficients. So here's the answer. In one specific case, when k equals 2, then d squared is 2. And then you get exactly the GHZ state. Another interesting case is you can think what happens when k is very large. This is semi-classical limit of Chern-Simons. In this case, d will become the dimension of the representation. In this case, it will be 2. So we'll have 1 over square root 3. So in the classical limit, it is a state in the GHZ class, but not exactly the GHZ state. And well, there's no obvious way of drawing a W state. So I tried different diagrams, and somehow you cannot produce it. So I'll tell you my opinion about this. So this is, I mean, you can still try. I haven't proven that W state does not have presentation in terms of diagrams. I mean, you want to have, you always can consider formal linear combinations of diagrams. So you can, of course, represent any states in terms of diagrams, but you want to be able to draw one single diagram, and with this, at least, you know, produce some characteristic state, some. Well, I don't know if anybody knows that. So it's a I mean, I think it is more like intuition. But maybe at some point it will be, it may become a technology. But so my comment here, I want to compare this also with quantum gravity and what people discuss in ADS-CFT correspondence. So actually, like last week there was a paper which with the title "There is no GHZ entanglement in quantum gravity," or no, quantum gravity not, in ADS-CFT in the classical limit. So there is no geometry in terms of ADS-CFT that can, which you can, create. So you cannot entangle, let's say, you cannot create a multi-wormhole, right? So regular wormhole is the analog of this state. So you have one end and the other end of the wormhole. You can think of, okay, can I create a geometry with this kind of state, tripartite? So the statement in that paper is that it is not possible. And in fact, you can also see this from Chern-Simons, that what will happen basically in the limit, so the limit that holography works, the ADS-CFT works, is you take the limit of coupling constant to 0, this is G Newton, which is the analog of taking k to infinity. This is the semi-classical limit of Chern-Simons. But what is also important for ADS-CFT correspondence is that the number of degrees of freedom is very large. And here you work with finite number of degrees of freedom. So this is a stronger situation than holography. So in this case, you can have GHZ entanglement, especially when k is small. So when k is small, k equals 2, you can get exactly GHZ state. But when k is large, it becomes sort of less of GHZ. So if you want to compare, if you want to create a large number of degrees of freedom in this theory, what you need to do, you need to put many lines. So there will be a state with, you should have 3 boundaries but connected with many, many lines, and that will mimic for you exactly the situation in classical gravity. Well, maybe not exactly, but it will be very similar. And then you can show that indeed you'll have expansion like this, but well, it will be multidimensional, so you'll have 0, 0, many zeros, many ones, many twos, many threes, and so on. But every other coefficient will be 1 over n suppressed compared to the previous one. So in the end, in this limit, you'll just get 0, 0, 0. I don't know how much ADS-CFT will be mentioned in this work. I will have a few more comments here just to remind you what ADS-CFT is and how this picture can be connected to ADS-CFT. But unfortunately, the take-home message here that, or maybe not unfortunately, so this kind of states, this is a certain, you should think of them as a certain resource in quantum theory. And then the question is, what is this resource good for? Well, probably this particular semi-classical states, and so the states in general, they are more classical than arbitrary quantum states. They are some sort of stabilizer states. So maybe one comment that one can make here, that in quantum information, there are these states called stabilizer states, and amongst stabilizer states, there are states which are called graph states. And as these diagrams here, which are, as I said, they can be classified by graphs and adjacency matrices of the graphs. These graph states, well, you can take a graph and you can map it to a certain state, which will be a stabilizer state. Stabilizer states are states which are invariant under certain subgroups of products of Pauli matrices. And they are important, they have nice properties for quantum computation. So there are different algorithms that are based on stabilizer states and on the fact that the states are invariant. So this is another resource like stabilizer states. They're not precise. I think they're not precisely the stabilizer states, but they might be interesting for maybe this kind of applications, like in quantum computation. Okay, so let me just again use this to discuss some more properties of quantum entanglement. And one, especially if you don't know what, you heard the word, but you don't know what this word means, so I'll give you some explanation. So what is monogamy? So monogamy is of quantum entanglement, is a property of quantum entanglement which states the following. So if there are two pair of states that are maximally entangled, let's say if A is maximally entangled with B, it cannot be entangled with anything else. And here you can see it like in this, looking at these two pictures, right? So you have A entangled with B, and the fact that it's maximally entangled means that, all the resource that A has, this correlation resource, entanglement resource that A has, it uses to connect with B. which means there's nothing else left for A to connect with C, unlike this case, for example. Although I just explained you that the two situations are equivalent, but this is just because this non-linearity of representation. You can, of course, build a more precise example. Right. Then, what about, yeah, so one comment about entanglement entropy, especially if, let me forget about more complicated state and focus on the states which are just the states with no intersections, which I use to classify entanglement in the bipartite case. So there is actually a simple way you can quantify entanglement in a special limit of these states. So if we just start with the maximally entangled state, what we have here is that the amount of entanglement is defined by the number of lines that connect the left and right. So how do we see that? Well, you can, what basically you can do a replica trick, and then you will see that maybe it's easier to understand if you just look at this other example here. Let's imagine a generic situation, and so this is you can think of the state, but this is also a reduced density matrix. So if you have a state like this, so to be more precise, I will want to put maybe more points and lines, because otherwise this example that I have here is trivial. But if I have a state like this, which has some lines that connect left and right, and there are some lines that start and end on the same boundary. So if this is a state, how do I compute density matrix? Well, I just glue two states together. They are obviously Hermitian matrices because they have the symmetry of left to right reflection. So if I just take the product of such states, I will get two closed circles here, and the rules that I explained before. When you can pull something out of the diagram and there will be no topological obstruction for that, you can just replace this by a number. So this two circles we can just replace by factor of d squared. So the density matrix is actually the same matrix as the reduced density matrix, is the same matrix as the original state, which is true for all kind of states which are used for classification. So then you want to compute any power of this, some power n of this matrix if you want to use the replica trick, right? But if you compute power n of this matrix, again, the diagonal will be the same, again, for the same reason. The only thing which will change is the normalization factor. So at the end, what you'll have that when you compute trace rho to the n, and well, it has to be normalized. So the only thing that will accumulate here is the normalization, which is due to the lines that connect left and right, that are not broken. So when you do the replica trick, the result will be logarithm of the dimension of something, of the subspace of the Hilbert space. But which subspace? Not the whole space, but only of the subspace which corresponds to the lines that connect left and right. So if here, for example, there are 4 lines, then it's a Hilbert space of 4 points. Again, that's dimension 2. So what is important for entanglement entropy, again, is just the number of lines that connect left and right. Well, if I compute this dimension, since it's a nonlinear function, this calculation is log of some Catalan number. But you can also consider a limit where this number of these lines is very large. And one more comment, so the general prescription, if you want to understand what is the entanglement entropy, I will put this. It will appear as trivial, but I will explain later why I want to do this. So I can just cut this diagram and compare different cuts. I can cut it like this, or I can cut it like this, or I can cut it like this. So or maybe like this. That's an even crazier cut. But each cut crosses a certain number of lines. But what is importantly, what will eventually compute the entanglement entropy is the cut that corresponds to the minimum number of lines crossed, okay, which is the one in the middle. So as I said, I can also look at this limit, so this particular limit when n is very large, but I also want to avoid degeneracy, so k must be even larger than n. In this particular limit, I can just take the Catalan numbers and apply Stirling formula and find that, well, the result will be that the entropy for 2n lines connecting left and right will be just counting, that will be exactly 2n times log 4. So in this limit where the number of lines is very large, I have this formula that, which is sort of trivial, so the whole situation is basically goes down to a certain number of Bell pairs that connect, that make the subsystems, and the amount of entanglement will depend on the amount of Bell pairs shared between the subsystems. But which is not exactly true when n is finite. Okay, now I'll just explain out some other properties just using this kind of diagrams. So first, the entanglement entropy is known to satisfy the property which is called subadditivity. So if my subsystem has if my system has subsystem A and B and possible complement of A and B, then the entropy of A and B is less or equal than the sum of individual entropies of A and B. So how can we see this in this formalism? So let me just draw these three systems, A, B, and the complement of A and B. Then I can assume that there are certain correlations between A and B. I will just count the number of lines that connect A and B. There are a certain number of lines that connect B to the complement and certain number of lines that connect an A to the complement. And then if I just write the simple relations for these lines, so the number of lines that is connected to A plus the number of lines connected to B is the same as the number of lines that connects to A and B plus twice the number of lines that connects A and B. So then this is obviously greater than n complement, which is just then, since in the specific limit when n is very large, I can just tell that well, this n is just proportional to entanglement entropy, and this inequality holds. So this is what subadditivity of the entanglement entropy means. It means that, well, so it means that the entropy of A and B together is not just A and B together is more let's say it's less than actually the sum of the individual entropy exactly because there may be correlations between A and B. And this number of correlations is actually, well, if we just compute what this L is, so L is called, which is the difference between left part and the right part. In information theory, this is called mutual information. So mutual information has this interpretation of the number of connections between two parties. You can also show how strong subadditivity is. This is a less trivial inequality that von Neumann entropy has to satisfy. So you can do the same exercise and you can show that this inequality holds exactly by a very similar calculation. So I'll not just go through this calculation here. So I mentioned that there is this interesting or maybe not so interesting limit of Chern-Simons theory when k goes to infinity. So what happens with theory in this case? Well, this parameter a that appeared in my skein relation goes to 1. So which means that this relation here, the intersection is just the sum of the two diagrams. So if I rotate 90 degrees, I apply this trick, nothing changes, which means that the permutation and the inverse is the same group. So the braiding becomes regular permutation in this limit. And what does it mean? It means that the lines can just pass through each other without interaction. So it's kind of non-interacting limit. So that k goes to infinity is the free theory limit of Chern-Simons theory. What happens with the entanglement in this case? Well, we can just look at these two examples. The first one, you have a loop that helps to connect left and right? So the left and right are connected also through this loop in the middle, but in the classical limit you can just forget about this loop, erase this loop, and then the state becomes not entangled. And what you should also notice here that in this specific limit, all possible states that I can draw here, they actually just reduce to this specific class of diagrams which are used for my classification, which are planar diagrams. By the way, I also use the word connectome to call these states because connectome is this terminology from neuroscience when they make maps of neurons and how neurons are connected with each other. So these are much more messier plots, but the idea is the same. Okay, the second example, again, you have some circle, but seems like a non-trivial configuration, but in the limit where you take k to infinity, you can just remove this circle and this becomes a maximally entangled state. So again, in this limit, the state reduces to this simple connectome type of diagram. So the advantage of Chern-Simons as compared to ADS-CFT correspondence and quantum gravity is that you can compute these entropies exactly. You can compute the leading order in 1 over k in the classical limit, and you can compute corrections. So here things are much more under control, and maybe this kind of calculation can be useful to, I don't know, study quantum gravity or understand certain effects in quantum gravity. So here, it is tempting to think of this simple class of topologies, right, these connectome diagrams, as some sort of classical topologies. So I just told you that I tried these topologies to, for example, reproduce certain quantum states, like W states in a tripartite entanglement, and I didn't manage to do this, and which is an indication that this state, this class of states, they are more classical than generic quantum states. So you have this kind of classical topologies. Here, by the way, the exact formula for one of the states that appeared in the previous slide, and you can see exactly what happens with this when you take classical limit when a is 1. So only the first term here survives in this expansion. So here, kind of naive interpretation of what you see is that, or what you want to see from this kind of diagrams is what these lines make. They sort of make, I will use this word, fabric of the space-time. So if you, especially if you take the limit when the number of lines is very large, then and I said that this seems to be similar to ADS-CFT correspondence. So these states should actually make, from these lines you can make up the space-time. And then in this classical limit there's no interaction, so this is kind of a free theory. So it's a classical, it's just space with nothing, but then you can turn on interactions a little bit. So what this will create, you know, certain fluctuations here. So maybe you should think of this as particles. And this kind of interpretation actually makes connection to loop quantum gravity. In loop quantum gravity, there is a language where you describe quantum states in terms of something very similar. The language is a little bit different because I don't know, I just prefer to work with spin 1/2, and they like to work with any spin. And then there is in quantum gravity, one of the description of quantum states is in terms of the so-called Penrose spin networks. So they also, it's a loop quantum gravity, so they don't like open lines, they prefer lines to be closed. And then you can start drawing a network where in this network every line has a different color and the color corresponds to the spin. And at every vertex you have to apply the rule of summation of angular momentum. So it is very closely connected to what I'm doing, because I said that I also can actually construct this particle with arbitrary spin, but in my case I just build everything by spin 1/2 lines, but I'll just need to apply some projectors. And then I can also construct this kind of spin networks, and this summation rules for angular momentum will come out automatically from the definitions of this projectors here. Okay, so comment about ADS-CFT correspondence. So in ADS-CFT correspondence, what we say is that we have two theories. One is called conformal field theory. It lives in some space of dimension D. And we say that this theory has an equivalent description in terms of high-dimensional gravitational theories, which is, which likes to live in anti-de Sitter space. The reason for this particular choice is that the space of isometry of ADS in D+1 dimensions is exactly the conformal group in D dimensions. So I can make connection of this diagram here, right? So there are two diagrams here, one which is just highlights that the space is kind of hyperbolic, so you can apply this styling, which is known Escher figures for hyperbolic space. But you can also use kind of fashionable, until recently, the tensor network construction of gravity in ADS space. But the idea is the following. So, you have a CFT, which in this diagram means a theory on the boundary. So you have CFT here. And then you have interior of this CFT, which is anti-de Sitter. And in some way, whatever happens on CFT can be reformulated in terms of something that happens inside, right, in gravity in ADS. So you call it a duality, right? So the description just in pure CFT terms is equivalent to the gravitational description. Well, it is gravity in a specific limit. Let me just show the details here. So when the Newton's constant is small and when the curvature is small, so this is exactly kind of limit that I was talking about. So you take k to infinity. This is taking your g Newton to 0, and you can take number of lines to be very large. This is like working with spaces with very small curvature. Okay, now I will just tell you that Meijer-Simons theory is basically the same thing, but I just fill my space inside, not with geometry, but with topology. And this topology can have certain features, and these features will encode which exactly quantum state that is my boundary theory wants to describe. Now I can apply, let's say, a local operator at the boundary. So this local operator at the boundary can be a braiding of lines, but this braiding of lines will be reflected in the boundary, so that in the bulk, in the volume of this picture. So if I apply something local, this means that I will have this additional twist for the lines inside. So this is the correspondence. The only difference is that, in mathematics we say that topology is more fundamental structure in manifolds. So you start with topology. Topology doesn't care about distances. And next level, you introduce a geometry. So you introduce distances. So here I can, I'm in this lower level than ADS-CFT in the sense that, okay, I only care about topologies. And in the case of geometry, you should think of how you can generalize this kind of picture, this kind of operations, but in terms of geometric quantities. And in fact, this connection between Chern-Simons and gravity is more precise. It's not, until now, I think it is not completely understood what is the connection, but at least in classical level, it makes sense. You can consider Chern-Simons theory with this gauge group SL2, SL2. It's a non-compact group. For this reason, the status of this correspondence is not very clear. But in three-dimensional gravity in NTD series space, you can map classical configurations to the classical configuration. And well, then the problem is that nobody still understands completely how you can quantize that and whether this connection really holds in quantum theory. But I think from what I told you, at least it makes sense to be true also at the quantum level. And there was a question in the first lecture by Pietro, who asked, what if I take k to -1 in my theory, and remember that you know, the parameters of my theory have k plus 2 in the denominator, so I'll have some very bad behavior in this limit. So what happens if I take k equals -2? So there were some proposals that if you take equals to -2, but with some imaginary part, which is proportional to inverse of the G Newton, actually you will get a gravitational theory. And it was just, you know, a conjecture based on calculations, some explicit calculations on some partition functions, simple partition functions, in two theories, in gravity theories, in three-dimensional de Sitter space, and in Chern-Simons theory with two SU2 factors, and it was claimed that the result is the same. Okay, so another connection with the ADS-CFT correspondence, so one like very celebrated results, which is actually also, I think, confirmed in loop quantum gravity, that the entanglement entropy, so if you look at the subspaces of your boundary, for example, I want to look at subspace A, region A on my boundary, and ask the question, what is the entanglement entropy of this region with its complement? So what the Rio and Takayanagi conjectured in, I think in 2006, was that in ADS-CFT picture you have to choose a minimal surface, and the entropy will be calculated by the area of this minimal surface. So you need to find the surface that which has the same boundary as the region A. It goes through the volume, through the bulk, but you need to find one which has minimal volume. And because of the geometry of this hyperbolic geometry, the minimal one will not be the boundary, but it will have certain profile inside. So then the entropy is given by this formula, and then you should somehow recognize my discussion here where I said to compute the entropy I need to choose a minimal cut. So here I could also have chosen different surfaces, but they would not compute entanglement entropy. I should choose the one which is minimal. Okay, so that's the connection. And then you can just, if you assume that every line is, you know, just a flux, which has a characteristic area of order G Newton, then the two formulas match. Okay, so the last part, so in the last 10 minutes, I will just quickly flash how you can use this kind of setup to discuss quantum protocols. If you somehow like it, you can look more in some recent papers that in my review, and also in the paper we wrote last year with collaborators, including students, by the way. So let me just discuss quantum teleportation. And the quantum teleportation, here's the very classic protocol for quantum teleportation. So you have two parties, Alice and Bob, and Alice has a state which she wants to pass to Bob. And to do this, they prepare the system in such a way that they share two spins of a Bell state. So Bell states, again, well, it states over there, and so one side goes to Alice, the other one goes to Bob. And then what Alice can do in order to quantum teleport her state to Bob, well, she does some preparation. So she applies some unitaries. So first one here is something called C0. I will not explain here what C0 is, but it's just a 4x4 matrix that guarantees that after this operation, the first two qubits get entangled. Then there's some additional Adamar gate that is applied, which basically make a convenient choice of basis for the measurement. Then Alice measures both of the qubits, and depending on the results, then she calls Bob and says, okay, I measure it, let's say, first in the spin up, and the second in the spin down, and then it just, depending on this result, Bob will apply a set of gates here. So in one case, it will be just X. Well, this depends on whether it will be just nothing if Alice measured 0, and it will be X gate if Alice measured 1, and similar thing here. So the result that after this protocol, what will happen, the qubit which was in Bob's possession will be converted precisely to this state psi that Alice had initially. Okay, so that's the normal protocol. So how do you do this in the TQFT setting? So first of all, remember that well, maximally entangled state, which is the Bell state, is this state here. So this is the qubit that Alice has. This is the Bob's qubit, and this is the state that Alice wants to teleport to Bob, and she doesn't necessarily know what exactly the state is. So this is just this black blob just means that there's any state here. So well, just naively, what you need to do in order to do this applied quantum teleportation, you just need to connect the lines. So what does this mean as an operation? Well, that's a measurement, that's a projector, so it just means that Alice, well, she better measure this pair in the Bell state, right? So if she is lucky and she indeed measures these two qubits, then what will happen exactly? The lines will connect, and the state will be, shifted simply to Bob. Well, this is not, of course, the full story. It is not guaranteed that this state exactly will be measured. So instead, there will be certain bases of states that will label the possible outcomes. So let me just say that there will be certain operations here that distinguish different basis states. So more generically, the situation will be this, where what kind of operations these BI are? Well, in order for this to be a good basis, these BI should be just unitary matrices. Unitary matrices are invertible, so the result of this operation will be something like this, but since these are unitary matrices, Bob can just do the inverse of these BIs, and this will produce the original state. And Bob will know which exactly BI the inverse to apply, because Alice will tell him, because she does the measurement, and she will determine which precise state the two qubits are. So unfortunately, in this setup, I cannot draw you separate diagrams for each of the basis states, and the reason for that, if you try to draw the diagram, two diagrams, in this more general formalism, which I use for arbitrary k, no diagram will be automatically orthogonal to the other diagram. So I can use the basis, but it will not be generically orthogonal, so you need to orthogonalize that. So in this sense, it is not such a nice result. But okay, if I just think of this as kind of stochastic way or classical version where I allow certain results to happen with certain probability, then the version, here's another version of this protocol, which resembles more the original protocol that I showed you in quantum information. So this is the state. So remember that what Alice needs to do first, she needs to apply a certain entangled operation that entangles this unknown state with the qubit that is entangled with Bob's qubit. So here is an obvious entanglement operation. You just exchange lines between left and right, so this should be an entanglement operation. And then Alice will do measurements, so there should be a set of projectors here. So this set of projectors you can choose in this way. This is not an orthogonal set of projections, so that's why it's a stochastic protocol. It's not really the proper quantum protocol. But it is just a nice illustration, so as a result, what you can see that if you just glue this kind of, for any two choices, right, for any choice of pair of measurements, if you glue this to complete this diagram, you will immediately see, after you follow the flow of lines, what kind of operations that need to be applied in order to, for Bob to receive this original state. Okay, so I'm at the end of my course. There's some conclusions which I try to draw out of this. Okay, so the main point that I wanted to probably achieve here or stress here is that TQFT gives you a certain way of representing quantum states, right? So and this way of representing, you need to draw a certain space, and this space, what it really does, it tells you what is somewhat the history of this state. So it just has the information of how the state was prepared from a, well, given some initial simple state. But think in this way, I think it also helps you to somehow, given a diagram, to read off what kind of properties the state should have, whether the state is maximally entangled, or is it separable, is it a projector, etc. And so in this particular model, I used knot theory, so that makes this exercise more fun. And I think it's a way to formalize certain intuition that already existed in quantum information theory. So people, of course, thought of drawing such similar diagrams in order to classify states. In particular, okay, if you want situation of two qubits, of course, this kind of diagram should tell you that the two qubits are not entangled, but if they're entangled, then this should be the proper diagram. Or if you go to 3 qubits, you can think of, this is kind of Bell state, generalization of the Bell state. This is probably should be GHZ state. Well, it doesn't also work very well with for W state, exactly for the same reason that, okay, here you use Bell pairs in some sense in order to represent your entanglement class, and this is not enough. And turns out that there were even more similar approach in quantum information, which is called categorical quantum mechanics. So you also can use category theory in a similar way, formalizing quantum mechanics, quantum operators, and so on, but which in principle is not related to knot theory. It is in some way more general. So knot theory is this is the approach of Bob Cook in particular and collaborators, which is also known as quantum pictorialism, and they like to work with slightly different realization using Pauli matrices. So instead of braiding that I use here, they use Pauli matrices, and this is also called ZX calculus. The difference of this approach is that the braiding in some way is more intuitive than just putting boxes in your diagram. So it is. I think it's easier to teach people what to explain to people what the diagram with braiding does than the diagram with boxes does. Okay, so I discussed quantum entanglements and properties. There are some more results in the literature. There's certain examples that I haven't discussed. There's an alternative way of constructing states with topology by a group of Balasubramanian, Robley, and the others, where instead of spheres they use tori, two-dimensional tori, and this is quite a different construction actually. And in particular, I do not know how this construction can be analytically continued to arbitrary values of k. So in spheres, there's no problem, just can do this for any k, but not in the case of tori. Okay, so yeah, I think that was the last slide. I think I'll stop here.
Okay, thank you very much. Questions?
Thank you for the nice talk. Maybe you can use your formulation for this infinite dimensional case, because even in the bipartite case, the SLOCC classification there's more classes than just counting the Schmidt number, I guess. And so maybe this Chern-Simons theory you are using, I don't know. Do you have some intuition?
Well, I think
why there should be, because there's like the infinite Schmidt number state. There are more than one class connecting two infinite Schmidt number guys, yes? In the bipartite case, so there's something there.
you can do something a bit more probably, indeed, maybe more fine classification. So here I mentioned, I think the proper slow classification just cares about number of non-zero Schmidt coefficients in the decomposition. But of course, every Schmidt coefficient itself has certain information, right? The entropy will depend. So you can try to make a more fine classification. And I think there are some, of course, you can think of the way maybe perturbative classification, right? So you start with these simplest diagrams, but then you can look maybe at the 1k expansion. So I told you that in the limit when k is infinity, the states are kind of classical. But you can also look corrections, 1 over k corrections. So this will be kind of perturbative corrections, which will give you some classification. I'm not sure you will get something interesting out of this, but this is some possible way of continuing. There's one thing which I didn't mention. This is related to possibility also to add non-trivial topological defects in the topology. So let's say I put some three-dimensional analog of a hole, which means my global topology will not be S3, but it will be something like S2 cross S1. So inside this S2 cross S1, I can cut 2 3 balls. So that will be, and I can also put some Wilson lines here, and that will be a certain state. And the property of this state, if I take classical limit for this kind of state, it will not reduce to one of the states that I mentioned before, because in terms of perturbation theory in K, the states like this, the states with just tangling of lines, they are perturbative. They all will go to this connectome class when K is infinite. But this is a non-perturbative state. There's actually a trick you can do to show that this hole can be actually created in a topology, maybe in a topology like this. If you start, if you put many lines in different representations here, you have to really have an infinite number of loops here, add an infinite number of loops, and this can be effectively substituted by different topologies. So this will create a hole. This is a non-perturbative effect, and well, this adding holes can also, it's a possible way to generalize the classification. And the general kind of intuition here, whenever you add a hole in your topology, in your space, it means you decrease connectivity. So in principle, the more holes you add, the less entangled the states are. So it's kind of at some point the space will break and it will no longer connect the two sides. That's kind of heuristic interpretation of topological defects.
Maybe it's like a kind of follow-up question, but can you extend this definition of classification? Can you extend the classification for excited states or even non-equilibrium dynamics in the TQFT framework?
So I'm not sure you need to define excited states because there's no Hamiltonian in topological theory, right? So what we really do here, we kind of on the ground state level, but this ground state level can have degeneracy, and we operate on this ground state level. So I'm not sure I can say something useful about the excited states. In some sense, if you think of, you can think of adding the hole as kind of creating an excited state. Because you can say, okay, there is an operator that acts on my state that creates a hole. Well, that's unfortunately not a unitary operator. But okay, creation operator is not a unitary operator. So then this is the excited state. So in principle, the same applies. In that sense, there's no really difference between ground state, excited states.
And another question is about the inequalities you have from quantum entanglement. It's clear for the quantum information theory what's happening, but in our case, from TQFT perspective, is that because of the underlying, I don't know, modular category or tensor category that's happening, or what is what is emerging to cause these inequalities?
Yeah, that's just, I mean, simple answer to that, these are properties of quantum correlations. Actually, the case I showed you is not very interesting in the sense that I reduced everything to just bipartite entanglement, and which in some ways is trivial. What you might be interested in is to understand how to really compute corrections and how to really see that the inequalities still work and what it really means when you include interactions. So this is kind of non-interacting case with very large number of degrees of freedom, but the inequalities should hold also for in any regime because they are proven for generic quantum states.
Thank you. I have a question about this emergence of spacetime. So you showed that from knots we can get the spacetime. Do you know, I mean, is it precise that you can have here one dimension or you can create more? So this would be first question. Please.
Yeah, so I didn't really show, right? That was kind of that's a part of the wish list. So it would be interesting to somehow maybe really build space-time with even gravity on top of this construction. And I don't think you need to really restrict yourself. Well, I'm not sure. Maybe it's only three-dimensional gravity. Because somehow in four-dimensional gravity, you will lose, in four-dimensional space, you will lose this property of knots to make knots, right? So just as I mentioned in the first lecture, every knot can be untied in
so you're not.
So I think it will be more like three-dimensional gravity, three-dimensional space-time.
So you would say that you already get three-dimensional, because as you say, these knots kind of, they live not in a space-time, yeah? They live...
No, so it's like discretization of space, right? So these diagrams are like a very, very discrete case where you do not see space yet. But now imagine you draw many, many lines. So altogether, they will behave like a space. You can also think of this actually as some kind of spin chain models, or maybe in a sense, I'm not again sure that I need to, whether it will be just effectively always one-dimensional spin chains, or I can make configuration for form any dimension. But maybe I will have to generalize the kind of interactions I use here, which are
because I
intrinsically three-dimensional.
I mean, this is maybe just a slogan word, but you know, there is this program, it from bit. So it's something maybe similar here that we get space-time just by doing the. In that case, this was just logical operations. So also how you tie the nodes. But let me go with the second question. So you try to convince us, as you say, that we have some structure of the space-time. I mean, topological. We could maybe speak about dimension. What do you think would be needed also to say that yes, now we have emergent differential structure?
I think if you know how to, I think if we focus on three-dimensional, not to be worried about whether this construction makes sense in other dimensions. So what you really start with is just discrete picture, and you need to understand how to take continuum limits of that. Oh, yeah. And then you will certainly have some differential structure, differential geometry. Which one? Yeah, I don't know. Oh, yeah. Whether it's generic enough to, describe any geometry, or you'll have very specific gravity in this limit.
Okay.
So, yeah, so here I have difference operators, which in continuum limit will turn into differential operators.
Yeah, if you say that you can have differential operator when we have spectrum, and when this, in a sense, not directly, but tells us about the differential structure of the manifold. Yeah.
I have to say that I know nothing about loop quantum gravity, but I just realized that probably it's almost the same thing. Well, in a sense that part of the mathematical formulation. I'm not sure how exactly Chern-Simons is connected to loop quantum gravity, but which I guess is defined in any dimension. Well, it's 3+1, right?
Yeah. Okay, so let's take the further discussion there, and thank again Dmitry. Дима, конечно, уедет, но людей совсем мало.
А потом все вместе.
А мы давай мы сейчас сделаем, а потом еще. Да. Тогда, наверное, объявит. There is some announcement.
A gente aproveita, faz uma foto do evento agora, aí depois cola com as outras fotos, aí fica bom.